Welcome back from lunch. I hope you've enjoyed the first two sessions and you're looking forward to the second half of the day, which, well, this morning was about the past, will be about the future. I'm here just for a moment to introduce our chair for this event and to hand then straight over to her. Liv Boeree is a science broadcaster and former professional poker player. With a first-class degree in astrophysics, Liv combined her science background and passion for games to become one of the most recognizable faces in professional poker. And since retiring in 2018, now focuses on education and specifically translating complex concepts into layman's terms, which is extremely successful. She's a keen philanthropist too, having co-founded Raising for Effective Giving in 2014, all of which makes her very firmly a humanist in deed and word. And we're very pleased that she can join us today to introduce and to chair this session. Thank you so much, Andrew. Yeah, hi everybody. It's a real honor to be able to chair such a fascinating session. It's a pleasure to introduce Stephen Smartt, who's going to be talking about our place in the universe. Certainly a topic close to my heart, and I imagine to many of you as well. To give you a bit of background about Stephen, he is a professor of astrophysics at Queen's University, Belfast. He got his PhD from Queen's and then went on to work at the Isaac Newton Group of Telescopes, which is one of the UK's overseas observatories in the Canary Islands. He then became a researcher at the University of Cambridge and mostly works on surveying the sky and looking for exploding stars, so looking for supernovae. Really cool. He has also won the Royal Irish Academy's Gold Medal in the Physical Sciences, and he was elected a Fellow of the Royal Society in 2020. And he has been a patron of the Northern Ireland Humanists since 2017. So pretty cool resume, I have to say. Yeah, can't wait to hear what you've got to tell us today, Stephen. Over to you.
Thank you, Liv, for that introduction. Okay, let me share my screen and get this working. So I'm going to talk to you today about our place in the universe and take us on a cosmic journey on what we know about our place on this Earth, in the solar system, in our galaxy, and what we know about the universe as a whole. It's really a topic that has expanded, and so this speaks to our origins. And what we as humanists want to find out about our origins. And it's really the last 100 years where this field has exploded, and the field of modern cosmology, of understanding where the Earth has come from within our local cosmic environment and the wider universe. And it's the technology advances over the last 100 years that have really made this science possible. So every civilization has had their own creation myths, and I really recommend Yuval Noah Harari's recent book "Sapiens: A Brief History of Humankind," which discusses why creation myths have been necessary for civilizations to exist coherently, to make decisions, and historically there clearly have been reasons why people have created these myths around the creation of everything that civilizations have seen, the important things to them, like the sun has been pretty important to ancient civilizations. Here's a papyrus from ancient Egypt, which has Ra, the sun god, which was the source of light and energy, and Ra produced these grandchildren, which were the earth god Geb and the sky goddess Nut. And this is a picture of the sky goddess Nut, which is overseeing her other deities. And so in somewhere like ancient Egypt, where humans obviously looked at the sky, saw the visible planets move, but everything else fixed, and the dark sky was a source of, obviously a source of religious inspiration to them. And that's evolved, of course, over centuries. But as humanists, that's not the creation myths that have been developed are just not enough, or they're not satisfying us. They don't satisfy our curiosity. And although we heard in the last session, humanist movement started in 1896, it was really back in the Enlightenment that our way of looking at the universe changed. And I say it's only in the last 100 years that we've really had the technology to test our ideas of our cosmic origins, the origins of everything we see in the universe, not just what we see on this planet. And so the great advances in physics in the 20th century were quantum mechanics and the theory of general relativity. Those are the two huge advances in the last 100 years in terms of our theory of how matter works on very small scales and very large scales. You don't need to know about those theories, the complex physical theories. I'm not going to talk about those in this 40 minutes. But all that I'll show you, all of the scientific evidence that I'll show you to put our place in the universe and our place in context are built on those foundations of both quantum mechanics and general relativity. But I want to convince you that everything that we now know about the universe just comes from doing something very simple, and that's looking, observing, and writing down what you see, and then repeating that process and having other people repeat the process to check that you were right. And that's fundamentally what science is. So, as I said, the way of looking at the universe changed in the 1600s with the Enlightenment, with the foundation of the Royal Society of London. So in that century, major things were the two major types of instrument were developed, and that's the telescope and the microscope. And here's a picture of what Galileo wrote down in 1610 when he used the telescope. He didn't invent the telescope, but he copied the technology that developed a refracting telescope, and he pointed it at the sky and recorded what he saw. And for the first time, when he pointed it at Jupiter, and you can see down in the bottom right corner here in this in his manuscript, that's a picture of Jupiter and its 4 brightest moons. And so what he saw was that the 4 brightest moons changed position and they orbited around Jupiter. And so for the first time, this cast on the Earth being the center of everything in the universe. For the first time, he saw something in the sky that orbited another body. These 4 little moons did not go around the Earth. They orbited around Jupiter. And then he also saw recorded the phases of Venus, which indicated that, again, the Earth was not the center of the universe. So that was applying the telescope to look at distant objects. And in the same century, the microscope was invented, and Robert Hooke's drawing of a flea is shown here. And so these two instruments allowed us to look at the universe in a different way and change our perspectives on the universe completely. And we do the same thing today. So here's a picture of an instrument at CERN, the particle collider in Switzerland. It's not a microscope, but it's an instrument that we use to probe the smallest particles that we know of, fundamental subatomic particles. This is the equivalent of the great advance of the microscope in the 1600s. And now we've got very powerful telescopes on Earth and in space, and this is an image of one here in Chile. This is an 8-meter telescope. We can fire lasers into the sky and correct for the distortion of the atmosphere and look at the very distant universe. But this is pretty much the same thing we're doing now as we started back in the 1600s. We're looking at things which are extremely small and trying to work out what the matter is made of, the stuff that we see all around us. What are its fundamental building blocks? And then we want to look at the very large and look at the largest, the objects of which are on the largest scale in the universe. And we use our ground-based telescopes and space-based telescopes to do that. And of course, the fundamental underpinning all of this is the scientific principle of trying to reproduce what others have done, trying to measure something new and have that corroborated by experiment. So if we want to find out what our place is in the universe, as I say, 2 ways of doing it, trying to work out what these tiny little things, what these particles are, the atoms that make up the molecules in our universe. And then we ask the question, what are the atoms made of? And the atomic particles like protons and neutrons, the next question is what they are made of. And so one way of the particle colliders that we built on Earth are one way of looking at matter. The other way of looking at it, pointing our telescopes to a random piece of the sky and asking the question of what is actually there. So when the ancients did this, of course, they were limited by the limitations of the human eye. When the telescope was first built, the next big advance came when photography was developed, and then you have a way of capturing more light. So our eye can't capture light over a long period of time because it can't take a 30-second or an exposure of 30 seconds or 20 minutes. And here is the deepest exposure of the sky which has ever been taken. It was taken by the Hubble Space Telescope. This is a tiny little bit of sky, which I'll put into context in a minute. But if you look at this, and this is a picture of the sky which had a total exposure time of about 600 hours, 25 days. So for 25 days, Hubble just looked at this one patch of sky and added up all of the images that it took. So it didn't actually open the shutter for 25 days, of course, but it took lots of individual short exposures, but it's the sum exposure time for this piece of sky was 25 days. It's called the Hubble Ultra Deep Field. And virtually everything you can see here is a galaxy. It's not a star in our own galaxy. So when you look at the sky, you see points of light. They're all stars within our own galaxy. If you pick a blank bit of sky and you look at it, and you look at it for long enough, this is what you see. In this image, there are approximately 10,000 galaxies in this image. Now, just to put that, you can see galaxies of different color, of different shapes, different sizes. These are all at different distances. The redder ones tend to be further away than the bluer ones because their light is redshifted, which I'll describe. But just to put this context, 10,000 galaxies. Look at the diversity and the complexity in that image. The size of that little patch on the sky that Hubble looked at. Here's a picture of the full moon, and that little pink square. If you think of the full moon in the sky, it's a pretty small region of the sky. I just want you to think of the area that the full moon covers. That little pink square is the size of this image. So Hubble has got a very small field of view. It looks in great detail at tiny pieces of the sky, and there are 10,000 galaxies, and so that represents the whole sky. If you imagine you could have that picture over the whole sky, the amount of galaxies are enormous. We think there are about 2,000 billion galaxies in the universe. The universe is made of these galaxies, and galaxies are just collections of stars. We're in a galaxy called the Milky Way. It's a spiral galaxy. If you picked out a spiral galaxy like this one near the top of the image here, our galaxy would be just one of those. And there are 2,000, approximately estimated 2,000 billion galaxies in the universe. Just want to show you a movie which gives you an impression of galaxies in the universe. This is made by the Sloan Digital Sky Survey and Berkeley Lab. So this is a fly. So this recreates how we think the universe looks like. The galaxies in the universe are distributed. Galaxies typically are separated from other galaxies by about 10 to 100 times their own size. So to scale, this is about right. And the images of the little galaxies you see flashing by are real images from surveys. So if you just look at the number of galaxies here, and this is just a little slice of the universe that is being recreated from real data. And I just wanted you to get the sense of the number of galaxies in the universe. 2 billion galaxies, and this should give you an impression of how many there are, and the sort of simple complexity of the universe. It's made up of things, and it's basically made up of a lot of galaxies. And so this just shows you and tries to convey the impression of how many there are. They're also, interestingly, not randomly distributed. They tend to be in clumps. So you can see there are little clusters of galaxies, and there are galaxies that sit along these filaments. So I'm going to show you a picture in a minute, which will show you the filaments. They're not just randomly separated in space, and that's mostly because of gravity and something called dark matter, which we don't fully understand what it is. But it gravitationally binds galaxies themselves together and stops them from flying apart. And it also binds clusters of galaxies together. So this was a huge project involving all of those universities and research teams that have just flashed past there. And it comes from what's called the Sloan Digital Sky Survey. Now, if I just take a slice through that the Sloan Digital Sky Survey, and you estimate the distance to those galaxies, this is what it looks like if you just flatten it down onto a disk and you take a slice through it. All this is the distribution of galaxies in the universe, and you can see it's not random. There are these clumps and voids and filaments. This is called the cosmic web. It looks like foam. Effectively, if you can imagine 3D foam and then taking a slice through it, and simulations of these galaxies which just come together under their own gravity. That's all that these simulations do. Can reproduce this, but you need a lot of matter in the universe, much more than we actually see from the light from these galaxies. And so the universe, a large fraction of the universe, is made up of what we call dark matter, which we don't fully understand. In fact, we don't understand at all what it is. But I'm going to concentrate on what we do see, the light that we do see from galaxies, and the stuff that we understand in this talk. So this is what our galaxies look like. 100 years ago, the science of cosmology and the science of understanding our place, or the place of the context of our own galaxy within the great cosmic web, it was started in 1915 by an astronomer called Vesto Slipher, and he only looked at 15 galaxies. And with those 15 galaxies, he took spectra of them, and that just split the light up into its different components. And he measured and discovered what is called cosmological redshift. So he looked at these galaxies and he split their light up into all its different colors. And what he found was of those 15 galaxies, 11 of them had their light stretched. So when light is emitted from these galaxies, what has happened when the light has traveled from the galaxies to us and into our telescopes, into Vesto Slipher's spectrograph on a telescope in Arizona, the light was stretched. So for 11 out of the 15 galaxies, the light was shifted to the red, it was stretched. And so how do we know this? So this is the most fundamental measurement that we now do in cosmology and astronomy. And this is a really simple and easy measurement. We look at the lines from particular chemical elements. The simplest chemical element is hydrogen. And the lines that we see, it's got a fingerprint. Hydrogen is an element that emits at particular wavelengths. And when we observe the light from these galaxies, it's stretched. So instead of the hydrogen lines being at 410 nanometers and 656 nanometers, which we measure in the lab, so the picture on the left, that's the wavelength of light we measure in the lab. Picture on the right is what we measure when the light comes from these galaxies, and everything is stretched. So that line, and all of the lines are in at the same position, just multiplied by a factor, and that factor is what we call the redshift. And so what has happened is that when the photon is emitted by the galaxy, as it's traveling towards us, and it can take tens of millions of years to reach us, space is being stretched. So all the galaxies appear to be moving away from us, but what is actually happening is space is expanding, and the photons of light, as they travel towards us, are being stretched. And we've made these measurements for 100 years now, and this is, as I say, the most fundamental measurement that we've made, and it tells us a lot about the universe. The objects that are further away tend to have greater redshift, so they have been traveling longer, and so the universe has stretched the photons more for those distant galaxies than for the nearby ones. And so this allows us to get an idea of how the universe is expanding, how fast is it expanding, and of course, interestingly, if every galaxy, so Slipher measured 11 out of 15 galaxies which had a redshift. They weren't at rest, nor were they blue shifted. Turns out those other 4 galaxies were just very nearby the Milky Way, and they were suffering distortions. Virtually every galaxy, when you look out in the universe, that picture of the Sloan Digital Sky Survey that I showed you, virtually every galaxy is redshifted. The light is redshifted. So that means every galaxy is receding from us. And also, we're receding from every other galaxy. You can work out, it's fairly simple to show that if we see every galaxy receding from us, if you put yourself on another galaxy in that distribution, they would also be receding. So every galaxy in the universe sees the same expansion. So if all galaxies are expanding away from us, they must have been much closer together in the past. And so this created the expanding universe between the 1930s and 1950s. Many theoreticians worked on Einstein's equations to determine whether or not there was a solution of those that would explain the ever-expanding universe. And the phrase "the Big Bang." So we know that the galaxies are redshifted; they're moving away from us. The universe is expanding. Therefore, it must have been much closer in the past. All the galaxies must have been much closer together in the past. Now, this term, the Big Bang, so perhaps it was created in an explosion. And this term, the Big Bang, was coined by Fred Hoyle, famous UK physicist, who didn't like the idea at all. Fred was one of the UK's leading physicists over the last 100 years. He didn't like the idea. Philosophically, he didn't like the idea of the Big Bang. So didn't like the idea of an explosive origin of the universe, an explosive origin to explain the existence of galaxies and all the stars within our own galaxy. So he came up with a rival theory called the steady state model, in which the universe was infinite. It had existed for an infinitely long time, and matter was created by an unknown mechanism. Now, it was a good theory, and it was a testable theory. It was just wrong, and it didn't stand the test of time. But it was actually Fred Hoyle who came up with the term "the Big Bang" in a derogatory sense, because he thought that the universe was not created in this way. So it stuck. The term "Big Bang" has stuck since Fred Hoyle came up with it and came up with his own theory to challenge the idea. And he held on to the idea that this was probably wrong until one measurement convinced him otherwise, and convinced other people who disputed the idea of an explosive origin of the universe. So the idea that galaxies are moving away from us is a clear and fairly easy measurement to make for even any student of astronomy now, with access to a small telescope. You can repeat these measurements. You can do the scientific thing and go out and measure the positions of the spectral lines of the elements, and you can see these galaxies are redshifted and therefore moving away from us. But one particular, going back to the idea of looking at the universe in a different way from the 1600s onwards, in the last 100 years has seen a revolution in us looking at the universe in a different way. And our own human perspective is biased towards optical light, of course, because our eyes work at optical light. But this is a tiny, tiny window on the physical universe. Visible light only covers a very small part of what we call the electromagnetic spectrum, which stretches from high energy gamma rays right through to radio waves. So you're familiar with gamma rays, radiation, which comes from, say, nuclear processes. You're familiar with X-rays, because many of you, I'm sure, have had an X-ray in hospital. Familiar with ultraviolet light, because I imagine many of you have been sunburned. You can't see the light that you get sunburned by. It's beyond the blue end of the light that our eyes are sensitive to. You are familiar with infrared light because you can feel heat. You've got microwave ovens, which you're familiar with, and you listen to radio stations. So you have experienced every form of radiation, or either experienced or have knowledge of every form of radiation that we know of. But our atmosphere only transmits a very small portion of this electromagnetic radiation. So what we'd like to do is look at the whole universe across every wavelength. And we've effectively done that. We've built satellites that are sensitive to gamma rays and X-rays and ultraviolet rays, and we've put them into space. We've built huge dishes on the ground, radio telescopes on the ground, which are sensitive to radio emission from the cosmos. But our atmosphere only transmits a very small region of this. But we've looked at the whole sky in all of these wavelengths. And here's the sky at 4 different wavelengths: gamma rays, And this was taken by the Fermi satellite, NASA's Fermi satellite. Here's a picture of the universe in X-rays. Here's a picture in optical, or more familiar light, and in radio. And so the thing, we've mapped the whole sky at virtually every wavelength, from gamma rays right through to radio, using different windows in the atmosphere and flying satellites. The interesting thing here is that this is just going and looking at the sky and saying, okay, so what does it look like at these wavelengths? What does the universe look like at these energies? And at all of these wavelengths, you really see objects that emit. And that's no surprise. There is one surprise at one wavelength, which I'll come to. But in gamma rays, you see these points of light, and you see this band across. In all of these, you see this band, and that's the band. That's our Milky Way galaxy. That's us looking through the disk of our Milky Way galaxy. But outside that, you can see all these little dots in gamma rays and X-rays. They're typically neutron stars, black holes, the centers of very massive galaxies. In the optical, it's mostly stars. And in the radio, you can see wisps of gas clouds in the Milky Way, but you can also see discrete sources. So the point here is that there are objects that emit radiation at all of the wavelengths that we know of, from gamma rays right through to radio. But there's one wavelength of light that is very peculiar and gives a signal which is totally different to everything else. And that's microwaves. So the whole universe glows in microwaves. So look at these. Well, everything here, it's pretty much individual sources that emit light in all of these wavelengths. At microwaves, it's totally different. The whole sky glows, and it's actually very smooth. Well, this is a picture of the sky in microwaves from the Planck satellite. And again, this is just about looking at the universe in a different way, with a different pair of glasses on, and with a different telescope at a different wavelength. And the whole universe has a very uniform glow, but only at microwave radiation. So what is this? Well, this image is probably the strongest evidence for the Big Bang, an explosive origin of the universe. So we're looking for evidence that our idea of the universe, that it's expanding, that it was created in an explosion, is true. And this image, because microwaves are very even across the whole sky with these little perturbations, but these are quite tiny perturbations on the microwave background. Effectively, this is a very smooth distribution, and it's very uniform across the whole sky. You get some colder and hotter spots, but those are much lower than the difference between the red and the blue here is much lower than the overall signal. So what's causing this, and why is it so important? Well, I think it's possibly the most fundamental, maybe the most profound measurement of the universe that humans have ever made. As I say, let me try and explain why this is so important and why it is real evidence that the universe was smaller and much hotter in the past, which implies there was some sort of explosive event that created it. And we're just using the physics that we use in our labs and you use at home. Radiation has a certain temperature. Now, when I say that, you might think, what does that mean? You actually do know this. You do have a feeling for it. So here's a picture of your oven. You know you don't want to touch that element in your oven because it's at about 800 degrees. And when it starts to glow red, you know it's on, and you know not to touch it. And so that has the light, it's giving off light. And so you know it's hot. You know from experience that it turns out it is about 800 degrees. But so that's something that you know of that's hot because you look at it in visible light and you look at it with your own eye. But if you go outside, you look at your car, you don't know what the temperature is. If you have a camera which is sensitive to infrared light, then you can measure the temperature of your car. So you can see the wheels are hotter. The overall temperature here, average temperature is 11.8 degrees in this image, but the wheels are pretty close to 20 degrees, and the engine is close to 20 degrees. You can see the roof's a little bit warmer because this car has just stopped, so heat is coming out of the car and it's rising and coming out of the roof. And the rest of the roads are at about 6 degrees. So the car has a temperature. this hot element has a temperature, which you know. And if you could see your car, if you touch your car, if you went and you touched the wheels, you would see that they're hotter than the ground, and the bonnet would be hotter than the road. So the radiation is telling you what temperature these bodies are at. And if you look, you can't see that temperature if you look at your car with your eyes, but you can if you look at infrared light. So this is what we're seeing at microwave radiation. We're seeing a temperature. It's very cold, and that's why we have to go to microwave radiation to see it. But we're seeing the temperature of the current universe. It's about minus 270 degrees, but that's what we're seeing. And the reason we know this, and again, I want to give you an impression, this is actually really sound fundamental physics that you can test in the lab. It's pretty much A-level first year physics can be used to understand the cosmic microwave background. Hydrogen, everybody knows hydrogen in the periodic table. It's the simplest of elements, one proton and one electron. If you have a photon comes in, you can break apart the proton and the electron. This is the simplest element that exists. You can have electrons and protons, which are free of each other. And if you do, then if you have hot hydrogen, then the photons interact with the electrons. If you break the hydrogen atoms up, then the photons interact with the electrons. They tend not to interact with the protons until you get to much higher energies and much hotter temperatures, because they're bigger and the electrons are smaller. So the photons end up interacting just mostly with the electrons, and that just creates a hot gas. And that's what we're seeing. That's all the cosmic microwave background is. It's just the temperature of the universe, but it's the temperature of the universe when it was much smaller. And because we know the universe has expanded, we're seeing the temperature of the universe from a very long time ago when it was hotter. So we know that temperature, we know the universe was hot, but we know the temperature at which you require, the temperature required to break apart protons and electrons. So we can see that the cosmic microwave background must have come from hot hydrogen. It must have come from electrons and photons, which are interacting with each other. But that needs a temperature of about 3,000 Kelvin. And so this is the other amazing thing about that image of the cosmic microwave background, is that if you take what we call a spectrum at any point in the sky, it's a perfect thermal emission. And by thermal emission, I mean it has got a single temperature, and the temperature is minus 270 degrees. So at every point in the sky, as well as being smooth, it's actually it's got a characteristic temperature. Now, this is a scientific plot that just plots wavelength of the light, and it's in millimeter wavelengths, as you can see here in the top axis, versus intensity. And the data points are measured with the uncertainty multiplied by 400. And the black is just a model from a body which emits at minus 270 degrees. So the other thing about, as well as the cosmic microwave background being very smooth, it's exactly what we call a thermal emitter at minus 270 degrees, which means because we know the universe has been expanded, we can trace back when that happened. And we know this was emitted when the universe was small and hot. The fact that it has this shape at every position in the sky, and it's only at microwave radiations we see this. We don't see this at all, at anything like this at other wavelengths. The whole of space emits at a temperature of minus 270 degrees. So this is and proof that the universe was smaller, hotter in the past. There was an explosion. The explosion we see, the radiation we see was emitted when the universe was 3,000 degrees C. And now it has expanded, and we're seeing it now very cold, because all of those photons from the early universe, which were hot, have been stretched, and now they reach us. So those are, as I say, I think maybe the two most profound images that we've made in the last 100 years, finding the relic of the Big Bang. And this has been repeated by several experiments that have been launched into space. So we see galaxies moving away from us. We see evidence that they were all closer together in the past and that there was an origin and an explosion. And it's very sound physics. There is no physics, there's no physical interpretation of the redshift of galaxies and the cosmic microwave background that can be explained without the universe being coming from an explosive start. It's a pretty amazing story, but it's very secure. But of course, we've got 98% of the universe is made up of hydrogen and helium, the two simplest elements in the periodic table. But look at the complexity. The complexity we see around us doesn't come from hydrogen and helium. It comes from the other elements that we see in the periodic table. It comes from the carbon that produces life on Earth, oxygen, the magnesium, silicon, sulfur, the iron in our blood, the complexity we have that we see on Earth, the rare Earth elements, the gold and the valuable gold and platinum that we have on Earth, and the diversity in the elements and the compounds that we see come from the richness of the periodic table. But the cosmic microwave background can only really have been hydrogen, a little bit of helium, but almost all hydrogen. So where did everything else come from? Well, there's hydrogen and helium in the periodic table. Hopefully some of this brings back either good or bad memories of chemistry in school. The two most fundamental elements, hydrogen and helium, actually, when you look at all of the universe, 98% of the visible universe, obviously we have dark matter, but the visible universe, 98% of it is hydrogen and helium. What about everything else? Actually, there's very little of lithium, beryllium, and boron in the universe. Carbon's the next most abundant, and then oxygen, and then neon. If you look at these, a peculiar thing is they're all multiples of 4. So here's if you look at the mass of these elements, so hydrogen has got 1 proton, so it's got a mass of 1. Helium's got 2 protons, 2 neutrons, it's got a mass of 4. And so just that, if you count all of those, the nucleons, as we call them, either protons or neutrons, if you count those as 1, weighing 1 unit, doesn't matter what the unit is, but call them 1 unit. Helium is 4, it's got 4 of those. Carbon's got 12, oxygen 16, neon 20. The next most abundant is magnesium 24. It's a multiple of 4. The next most abundant is silicon 28, another multiple of 4. Then sulfur 32, argon 40, calcium 40, and then iron 56, which is also a multiple of 4. So this is what Fred Hoyle recognized in the 1950s, that these elements could be built up from burning helium, so fusing helium together, putting helium nuclei together to create carbon, then oxygen, then neon, because they're multiples of 4. And so the elements are built up in stars. So when the Big Bang happened, there was hydrogen, helium, trace amounts of lithium, and the other elements that we see now were all built up within stars since galaxies and stars were created. How do we know this? So again, this is something that which has been proven now by theory. It's something that I've worked on for a while, and the origin of the elements and where they've come from. We really want to know where oxygen comes from. It's essential to life. Our Earth is dominated by oxygen. The oxygen in the water, and that is essential for life. The oxygen in the air, which is essential for life. We'd like to know where that oxygen actually came from if we want to understand our cosmic origins and what are the reasons that life evolved on this planet. So we do have an idea of the universe being created in a Big Bang. Galaxies formed out of that as the universe expanded. In these galaxies, you have stars, and around at least one of these stars, there are planets, and that's our own solar system. So if you look at our galaxy, if you could look at our own galaxy, this is the galaxy M61 in the Virgo cluster. Look at the complexity here. Compare it with the simplicity of the Big Bang, where it's hydrogen and helium. Something has happened in the time since the Big Bang, where there was really only hydrogen, helium, and a trace amount of the other lighter elements. To create this complexity. So these galaxies are full of the elements in the periodic table. So everything that we see, we haven't never detected a sign of an element that's not in the periodic table. We're dominated by oxygen and carbon, magnesium, silicon, sulfur, iron and calcium. Those are the dominant elements in every galaxy that we look at, and every star that we look at, and every galaxy that we look at. There's differing amounts of them, but they're the dominant elements, apart from hydrogen and helium, which are 98%. Those are the dominant elements, and they give rise to this beautiful complexity that we see in galaxies. Our own galaxy is something like this. In our own galaxy, there are 100 billion stars. Some of them are more massive than the sun, some of them are less massive and cooler. But in these galaxies, if you look at these galaxies, so we're asking the question, where did all of the complexity come from in our universe and in our galaxies? It turns out a lot of the chemical complexity has come from exploding stars. And so we see these exploding stars happening, and this is what I do and my group does, and the teams that I work in do. We survey the sky on a daily basis, and we look for things that pop up that weren't there before. So here's an example. Here's a nearby galaxy. It's another very famous galaxy, M74, Messier 74. Here's images taken by two different telescopes. The one on the left is the Gemini Observatory in Hawaii, and the one on the right is a telescope in Chile. And you can see there's a very bright object that pops up in this galaxy. This popped up in 2013. It's not in the one on the left. So this was about 10 years later that this image was taken. We now survey the sky every few nights. But you can see there's a new star has popped up, and this is a supernova. This is a massive star that has exploded in this galaxy. And stars have lifetimes like we do. They're born and then they die. They just last much longer than humans do. They last something like, the most massive stars can last somewhere between 5 and 40 million years. So what I want to show you is the clear evidence that these massive stars produce the oxygen and the heavy elements that we see. It's a fairly simple thing to do. I'll show you this little movie of every supernova that humans have ever discovered since Tycho first saw a supernova in our own galaxy back in 1604. And so this was put together by Isaac Shivers, a postdoctoral scientist at UC Berkeley. And so this just shows you a very rapid run through the last 400 years of every flash there has ever been in the sky. And so we see these flashes happening all the time. And these are the things that create the chemical elements, the heavy chemical elements that we see in the periodic table. We see them popping off in these galaxies all the time. And for a small number of them, we can go back and we can actually see the star that exploded. And so these stars that these are from massive stars that are forming in nearby galaxies. And here's an example of 1008. We saw a supernova in this galaxy. But interesting, this galaxy had been observed before the supernova exploded. And if you go back and you look at, what was there 7 years before the explosion, an image of this galaxy, a really good image, was taken by a telescope in Chile. There's a little red star at the position of the supernova explosion taken before. And so that's exactly the star that exploded. And if you go back 2 years after, and we did this, you can see that red star is completely clear. So that definitely did explode, but you're left with a little green, blue type light here. That depends on how you combine these images and make the color, but you can see the star is gone and we're left with that. That's actually the oxygen, which is glowing. The oxygen that was produced in the supernova explosion by the massive star is glowing at the position that the explosion happened in. So how do we know that it's oxygen? It's exactly the same emission as the aurora that we see in the sky. So we see the aurora at the northern and southern poles. And this, we can repeat it in the lab, of course. But this green and red light in the aurora is oxygen, which glows at very high heights in the atmosphere. And that's exactly the same signal that we see left over after the supernova exploded. We just see a lot of it because it's produced a lot of oxygen. And so that oxygen was cooped up in the star while it was living. And then right at the end of its life, when it exploded, that is being released to the galaxy. So that oxygen that we see, the oxygen we see in the aurora, the oxygen you breathe in the Earth's atmosphere, was created in stars in previous generations and stars in our galaxy in these supernova explosions. So the final thing I'll come to is just the our own solar system and the uniqueness or not of our own solar system. We've got a galaxy full of stars. If you look in, you can actually see stars forming. This is one of the probably most famous images taken from the Hubble Space Telescope of the Eagle Nebula. The blue colors here represent emission from oxygen. The red is sulfur, and the green represents nitrogen and hydrogen. And to give you just an idea, if you just look at the little ear on the top of one of those pillars, and you look at the finest detail that you could possibly see, our whole solar system would fit within that comfortably. That's the size of this star forming region. And so this is dust and gas, which is about to form stars. And the reason we know that is because we can actually take images of stars being formed. This is an image from the ALMA telescope in Chile. This is a picture of a young star with a disk around it. And for the first time, and this is at radio wavelengths, we can see the disks of stars which are probably forming solar systems and forming planets in our own galaxy. And this is a pretty stunning image, and that distance there is about the Sun-Jupiter distance. So we're really starting to probe in other systems the scale of our own solar system in other stars. I'll just finally leave you with we've not only detected stars which are dying and stars which are forming, but we can actually see planets going around other stars. This is a rendering of how we detect planets around other stars. You never see the planet, but you see a dip in light as a planet goes in front of a star, and so you see a little shadow cast by the planet. And over the last 20 years, more than 4,000 planets have been found around other stars. Nobel Prize was awarded last year to the discoverers of the first exoplanet, the first planet around another star. There are only 4,000 planets known, but there will be millions, if not millions, out there in our own galaxy. So if we ask the question, is there another Earth in the Milky Way with life? So we know there are 100 billion stars in the Milky Way. They've all got chemical elements like our own. That's 10 times 10 to the 9. What's the chances of one having life? So to get life, we'd need a star like the Sun. Let's say that's 10%. Now, all of these numbers, I don't know, but it doesn't really matter what the number is. It's somewhere between 0% and 100%. Let's say it's 10%. That's not a bad guess for that number. Let's say those Sun-like stars have planets. Let's say they're 10%. Only 10% of those have planets. Again, it doesn't really matter exactly what that number is. It's not 0 and it's not 100. Let's say 10. It might be 20%. It might be 30. But I'll show you that doesn't really matter. Stars need to have an Earth-like planet if life is going to exist. Let's say there's a 10% chance of that. Let's say there's a 10% chance of them being in the Goldilocks zone. It's not too hot and it's not too cold. Let's say there's a 10% chance of them being dynamically stable, so the big planets don't knock out the inner planets when these are forming. These are all things that have had to have happened in our own solar system for life to have evolved. Let's say the Earth-like planet has to have water, and it's 10% chance. Let's say it has to have a moon. You might think, why do we need a moon? Well, when our amphibian ancestors crawled out of the oceans, the moon helps the tides happen, so it helps life evolve in the interface between Earth and between land and water. Let's say there's 10% chance you see life. Let's say there's a 10% chance you don't have too many asteroid or comet collisions that wipe out civilizations. Let's say there's only a 10% chance that an intelligent civilization evolve. Still a pretty good chance. And let's say there's a 10% chance that civilizations don't destroy themselves. That implies out of the whole of the number of Earth-like systems, or of all of the stars in the Milky Way, there might only be, if you multiplied all of those probabilities together, you get 0.1 times 10 to the 11, multiply that by the number of stars, there might only be one Earth in our whole galaxy. Now, the point of this is that I don't know, most of us don't, not many of these numbers are well known, but it's reasonable that they're a few times 10%. And that means it's possible that an Earth-like planet with life on it in our galaxy is actually quite rare. And a number of people have done a much more sophisticated calculation than this and come up with a similar idea. It may be that some of these numbers are completely wrong and it's 100%. And so the number of Earth-like planets may go up in our galaxy, or the estimate of the number, but it might be. It's not unreasonable to suggest that our Earth is quite unique in our own galaxy. But of course, there are 2,000 billion galaxies out there. So let me leave you with the conclusion of our cosmic story. Our universe is expanding. It's full of galaxies like our own. And this is our view, our humanist scientific view of the universe and our cosmic origins. The universe glows in microwaves. It definitely was smaller and hotter. The Big Bang happened in some form. We don't know why it happened, but an explosive event created the universe, almost certainly. Models of the age of the universe suggest it's 13.5 billion years. Our stars in our galaxy are 11 billion years old. And the sun and our solar system are about 4 billion years old. We see stars forming, and we've detected exoplanets around those other stars. But thank you. I'll finish there.
Thank you so much, Stephen. That was absolutely fascinating. I particularly loved your demonstration going through the sort of the 10% multiplied by the 10% and 10%, because it's quite a counterintuitive concept. You know, it's because we know there are so many stars just in our galaxy alone. It seems mind-boggling that we might be the only sort of intelligent civilization here. Given that, I mean, I by and large agree with you that I think we might be, that the Earth is an incredibly rare place and aliens are incredibly rare. Given that, what sort of, you know, what philosophical implications do you think that carries, particularly about our future?
Yeah, so I think for now, particularly as we are suffering a climate crisis on our own planet, and there is no planet B, it really emphasizes, I think it should emphasize to everyone how precious our own planet is. Yes, there are 100 billion stars in our own galaxy, but the fact that there might be life of this sort only on this planet, or a very small number of them, I think it really gives us an impetus to take care of this precious place. That's my immediate take on it.
Yeah, I very much agree. Given we've only actually got a minute or two for questions, so I'll ask one more. You've dedicated your life to research about space, and there are still so many unanswered questions. So if you had to pick one question that you had to find out in your lifetime, the answer to one of these, you know, whether it's the source of dark energy or dark matter, whatever it is, what would it be?
I'd say probably what is dark matter? I think it's something which has bothered everyone for such a long period of time. There's so many implications for both fundamental physics and the universe in the discovery of what dark matter might be. Or is it that the general theory of relativity is our theory of gravity wrong? Is it a fundamental particle? Are there little black holes out there that are what we call primordial black holes? I think the discovery of dark matter what it is will probably revolutionize physics in some way that we don't appreciate yet. I suspect I think that's the most interesting thing from the physics point of view. I think the big question is, is there a planet that looks like it might have life on it? And that's obviously, or could we find life within the solar system, even primitive life forms existing on Mars or in the oceans under Europa? I think that's probably would have more impact on human civilization. For physicists, it's sort of dark matter is, what is stuff really made of? What is most of the universe actually made of? Probably a bit boring for most people, but I think as a physicist, that's the big question.
Yeah, it's certainly must be quite a frustrating thing, knowing that there's just so much stuff out there that we just don't know where it is and what it is, and what is causing it. I've just been told we have an additional 5-10 minutes for questions, so great.
Okay.
You mentioned that about the original sort of battles that sort of Copernicus and Galileo had to sort of fight against, about convincing people that actually, you know, the Earth isn't the center of the universe, and actually it looks like everything is going around the sun. they were fighting against this sort of, I guess, groupthink. I mean, I guess it's not even really a scientific consensus. It was more a religious consensus. But it's interesting, this idea of sort of groupthink and how it is often in all sorts of fields of study. Do you think there's any topics in astrophysics that you suspect there might be that phenomenon going on at the moment?
I think everyone suspects. So we have this idea of the standard model in cosmology, and I think even cosmologists are a little bit concerned that they have come up with this, which they don't think is the true theory. They think it's maybe a reasonable representation of the true theory, but they do recognize the groupthink aspect of that, is that they all do the same calculation and come up with the same answer, is that this is quite a good theory of the universe. So the Big Bang, dark matter is influencing galaxies. Then there's dark energy, which is pushing the galaxies apart a bit faster. And so that standard model, standard cosmological model, works quite well, both in the computation. If you go into the detailed computation, it works well. But the cosmologists themselves are not convinced that it is the true full picture. And they do recognize this idea of groupthink, as you highlight, and so, but there hasn't been the creative thought of how that might change, and that will probably be driven by another discovery, because everything is working quite well with this model. It's not until you make it an experimental discovery that you break the theory. So I think that's where, although this standard cosmological idea that I sort of presented here, the overview of it, works well, maybe there is something else to it. This is an approximation to the truth.
One of the questions that's always on my mind about the universe is how, if any of the many physical constants, the speed of light, binding energy, and so on, or of chemistry and physics, were just a little bit different, it would be a drastically different place, and very likely that complex life like us could never have emerged. Mm-hmm. So and this is often used as a sort of a proof for God, and this idea that it must have been designed in some way for us. Are there any other possible alternative explanations for why our universe looks so well made for us?
I think the answer is no. No. I think what you're asking is there any reason why the speed of light is 3 times 10 to the 8, or the gravitational constant G has that value? I think the answer for many of those is no. There isn't. There doesn't seem to be a fundamental reason why that is. There's the anthropic principle in that if they weren't, well, we wouldn't be here to as you say, we wouldn't be here to measure them, to measure those values. And therefore they had to be like that for us to be able to measure them. It's not a very satisfactory answer at all. But I think even if there are discoveries in dark matter and dark energy, that question of why is everything just so perfect for us? I certainly don't know the answer to it. I don't think there is any good explanation for why all of the constants line up and just give us the perfect conditions.
It could be that. It could be that there are multiverses, and that because we would naturally, where actually every possibility is, or most possibilities are fulfilled. It's just that, as you said, we can only be in the universes to observe and measure these variables, well, not variables, these constants, and thus observe the ones that seem well made for us. Yes. Some questions from the audience, from an anonymous attendee. Into what place or space are the galaxies expanding?
Good. So this is a great question. So think of this analogy, because you cannot think in the extra dimension that you need to do it. So our universe is expanding effectively in four dimensions. It's the 3 dimensions of space and 1 in time, and you can't envisage it. But here's what do you need to envisage? Think of a balloon, the surface of a balloon, and of that expanding now. Think of just being on the surface of the balloon in 2-dimensional space. So think of you being squashed on the balloon, right? You've only got 2 dimensions. The surface of the balloon as it's blowing up is expanding. It's not expanding into anything. It is in 3 dimensions, but that's because you've got the extra dimension. But just think of yourself as a 2D being on the balloon. The balloon is expanding. Everything is moving away from everything else, but it's not expanding into anything. The whole thing is being stretched. Space on that 2D surface It's being stretched. So that's the analogy you have to think about. You cannot, and I can't, and I've never met anyone who can think of the same analogy in 3 dimensions. Your mind just can't do it. So you've got to think of the 2-dimensional surface being an analogy for our 4-dimensional expanding universe. And think of that. It's not, there is no center to that expansion. You might be the center of the balloon, but it's not for the 2-dimensional surface. The whole thing is expanding without having a center or expanding into anything else. You have to think of the analogy.
Yeah, it's mind-boggling, is it? Because you have to be able to picture it. You have to be able to visualize in four or higher dimensions, and we just can't do that.
Yes, you can't.
Unless you're in certain, I don't know. Some people claim they can, but I've tried many times. I've not succeeded. John Sniadowski asks, do you think we might be in a simulation?
Simulation. So I would have to say no, unless whatever is created, that simulation is able to connect, all of our consciousness in some way and force us to communicate. No, I don't think we're in a simulation with, say, predefined outcomes. No, would be my guess, but I guess there's no way of proving. There isn't an easy way of proving that wrong. But my guess is not.
Isn't the latest thinking that our universe is deterministic to an extent? I just remember reading Sean Carroll, and he was saying he was giving the argument that it is.
Okay, so I've always assumed not because of the quantum uncertainty principle, and you can't predict. At that level, you can't predict the future, even given a very well defined system at the start. There's fundamental uncertainties that you have because you can't know the position and the momentum of every particle in the universe. And so therefore, even if you did know the original conditions, you'd never know it to precise enough, the conditions to precise enough values to be able to predict the future.
Right, there's like this
a very powerful computer because there's an intrinsic uncertainty.
Right.
Sean Carroll's very, very smart guy. I should read what his latest view is on that.
Yeah, I have to say I agree. I couldn't quite marry the uncertainty principle into that. I don't see you could have a fully deterministic universe, but I mean, it's possible that a simulation could have sort of starting conditions, starting parameters set, and then you just sort of press play on it, and then it evolves and unfolds in a way that wouldn't be that dissimilar to our universe. I think, unfortunately, that is all the time. Maybe we have time for one more question. Okay, Ian asks, do you believe in time travel?
I believe so. Not for beings like us of our size. I think it may be possible for very small particles in some reasonable time scale. That very small particle, we may be able to manipulate the travel of very small particles, particularly the idea of quantum entanglement, where you have 2 particles which are very much separated, but when you change the state of one, the other immediately changes, and but that's faster than the speed of light. So I think that's sort of the equivalent of time travel. So I think in maybe not too distant future, that effective, it's not quite time travel, but effective time travel may be captured in some way, but mostly for very small particles, it's a big jump to go to things like us.
Yeah, and presumably if backwards time travel was possible, we'd be being visited by travelers from the future all the time because and they've been messing with everything, and yeah, it doesn't seem like it can work.
Yeah, maybe they have.
Yeah, who knows? It's one of those sort of unfalsifiable hypotheses, I think. But brilliant. Well, Stephen, thank you so much. This was absolutely fascinating. Thanks to everyone for all the questions. Sorry we didn't get time to them all. But yeah, this is really, really mind blowing. So thank you.